Hello all, and happy 2015 to everybody. It's time for the first update in quite a long time on my homebrew Z80 computer project. Today's video is mostly going to be about some software work that I've done for this machine, the LM-512. The hardware has not changed appreciably since my last video. The hardware side of it is pretty much done. There are a few small things like a beeper or something that I might still add, but the bulk of the work is done. I guess that the only thing I've added since last time that'll be of interest in this video are some LEDs. So there used to be LEDs on the CF to IDE adapter for power, whether or not there was a card in the adapter and whether or not there was any disk activity. I found those LEDs to be sort of really stupidly bright to the point that it was distracting, and so I've actually ripped those out, and there are a bunch of LEDs on the LM512 itself now. There's a red one on here which you can hopefully see is on. That's to indicate power. There are two green ones here which are under software control, as we'll see later, and there's an orange one which is also currently off, which is for disk access or CF card access, and we'll see that working as well. So I'll zoom into my terminal now. I'm just running GNU Screen in an Xterm, and it's connected to the LM512 via a serial cable. I've actually got two serial cables linking the LM512 with my PC in this video. One of them is used for the command line interface, and another is used to transfer data, as we'll see in a little bit. So yeah, I'm gonna reset the LM512 now, and okay, we see this message on the terminal. Welcome to LM512 Microcomputer System. So in all my previous videos, I've actually had a very small, very simple program, the same program the whole time on the ROM chip in the LM512. So that's the firmware, or the BIOS if you like. And that was a super simple firmware that did nothing but read the first 256 bytes off the CF card, copy that straight into RAM on the LM512, and then execute it. And so whenever I did one of my other videos, I would just write the program to demonstrate whatever I wanted to demonstrate in that video. Make sure that it was less than 256 bytes. Write it straight to the beginning of the CF card using the DD command. So there's no file system on that CF card. I'm just writing to it sort of raw. And then the LM512 would boot that, and that was it. And so, this is the first video where I've actually got some significant software on there. I've actually got a little 4K, monitor program on there. When most people say monitor these days, they're talking about, this thing, your screen. But historically, monitor was also used to refer to a very small and simple program which would let you monitor the operation of the computer at a very low level, at a kind of memory level. And so this is a small simple monitor that I've written up, and it exposes most of the basic functionality of the computer in a pretty low level way. So like I said, this is the command line interface. I can type in hello YouTube on here and press enter, and it will say what, because hello YouTube is not one of the commands that the monitor understands. But if I type in help, I can get a listing of all the commands that it does recognize. I'm going to make this terminal slightly larger so that it doesn't wrap as much. I guess you guys can read most of that. So there are a whole load of commands here, and I'll demonstrate most of them. So I guess sort of beginning at the most elementary level, we have peek and poke commands, which will be familiar to anybody watching who used 1980s era home microcomputers. So peek and poke are just they're basic commands, basically the programming language, basic commands for memory access. So if I type in peek 0000 and hit enter, I get back 31. So this is showing me that the byte stored in the LM512's memory at the address 0000, i.e. the very first byte, is 31. That's hexadecimal output 31, so it's 49 decimal. But that is the first byte that's in the address space, so it's the first byte of the ROM in this case, because the ROM is mapped to the top of the address space. And so if I keep going, peek 0001, peek 0002, what this is, oops, easy, not E, peak, what this is actually doing is showing us, you know, the bytes of the program that this modeler program that's currently executing one at a time. You know, so we can see the first bytes, so, you know, 310080C3. And a peak's counterpart is poke, which lets you store a value. If I try and poke the value 42 at address 0, and then peak there, we'll see that it hasn't changed. Peak's you know, 0000 is still getting us back 31. So remember that this you know, bottom of the address space is the ROM chip. It's read only. We can't write to it. If I peak somewhere further down in the address space, say you know, at 4000, which is 8 kilobytes into the space, and we can see the value A8. If I poke 42 into 4000 and then peak there, you can see we're actually getting back 42, not A8. So the memory has actually been modified because this is RAM and we can modify it freely. This is kind of very basic, very low level memory access. And these were the first commands that I wrote for this modeler. I've actually got a much kind of nicer way to access memory now. There's a dump command. If I go dump 000, this will actually dump out the first 256 bytes, or 256 bytes after the address you specify. So in this case, the first 256 bytes in, you know, a nice little hex editor format. And so you can see this is the machine code for, or the beginning of the machine code for this program, and by pressing space I can kind of continue and sort of page through memory as far as I like, and I can press Control-C to get my prompt back and do something else. So it's, you know, pretty easy to see what's happening in memory. And there's also a memed command, which is for memory editing. This lets you change what's in memory 1 byte at a time. So starting at address 4000, currently has the byte 42 in there. I can change that to say 00112233, you know, dead beef, everyone's favorite hex constant. And I can just keep modifying memory until I'm done. I can hit Control-C to abort that, and then if I dump out 4000, you can see the top here, you know, 0011, blah blah, you know, there's our dead beef. That's modified memory. So, you know, memory access is actually pretty convenient now, which is pretty great. What other commands do we have? So I guess real quickly, there's a date command now, which gives you the time on the real-time clock. This is the first video in which the real-time clock actually displays the real time, because you can set it now using you know, a nice long decimal string, same kind of string you use for the Unix date command. So you start off with the year, which is 15 in this case, the month, January, the day, it's the 2nd, and then you can put in the time. So let's pretend that it's 6:15 in the morning, and oops, I've forgotten the seconds, so we get a nice little error message there. 6 AM 00, bang, okay, so now it thinks it's 6:15, and it tracks the time since then. Let's stick it back to the actual time, which is something like 3:47, 59 seconds PM. Okay, now we're back on the actual time, or near enough to it. This clock actually drifts an annoying amount, you know, it's drifting something like 10-20 seconds a day. I think maybe the 32 kilohertz crystal I picked might not be of the correct specs for this chip. The capacitance or something might be wrong, so I'm gonna have to look into that, because it's drifting, you know, to a pretty shocking degree. But you know, it basically functions. There's your date command. Oops, you'll notice I typed in hell then and not help. The help command still ran. The way the string matching works is that you know, you can type a partial command and it'll match the first thing, which matches what you've written so far. So you can actually you know, you can abbreviate peak to PE if you like. You can get, you know, some fairly terse things. Let's see. Right, so we've got in and out commands, which just do input and output on the Z80's I/O pins. So as an example, you know, I'm going to show you the software-controlled LEDs. So I'll zoom out again a little bit. You can see that the two. Oh, can you? Yeah, you can see them. The two green software-controlled LEDs are actually both on now. I'm not quite sure why they're both on. They were off when this Oh no, so they come on. They come on when I restart. They're on by default. So they're hooked up to some of the general purpose output pins on the UART chip, and so I can use the out command. The port for E is in a register on the UART chip, which it lets you set to 0 individual bits of the output. So if I type in FF, I'm telling it to set all bits to 0. And if I do that, the LEDs go out, there you can see. And I can use the out command to address 4F, which lets me set things. If I set 80, I get one of the LEDs on. And if I set, oops, easy, butterfingers, if I type 40, other one comes on. You know, and I can reset them individually, blah blah blah. So they're under complete software control, and so I can, you know, programs can do whatever you want with them, which is pretty nifty. And there's a corresponding in command which reads in a byte, but I can't really demo that because I've got nothing hooked up to kind of provide input. What else have we got? I guess the other. Well, there's a jump command which just you know, sets the program counter to a particular address. So if I type in jump 0000, this is basically a restart of the system. There we get our welcome message again. It just goes back to the beginning of beginning of ROM, and begins executing from there. And so you can jump around all over the place, and I'll show you an example of that later. But I guess the only other major commands I haven't shown you yet are to do with the CF card. So we have a bunch of commands to deal with the CF card, and I guess I'll show you CF save first. So the CF save command, you know, saves data from the LM-512's memory to the CF card. It takes a CF card sector as its first argument, which is an 8-digit long hexadecimal string. So this is just the first sector on the disk, you know, 8 zeros, and I'll start from the beginning of memory space in the LM-512, 4 zeros, and the final argument is the number of sectors you want to write. So each disk sector is 512 bytes, and so if I put in 80. That's 128 disk sectors, which is actually the is 64 kilobytes. It's the entire addressable memory space of the Z80. So when I hit enter on this, it's going to save all 64 kilobytes of the computer's memory to the CF card. I'm going to zoom out so that you can see the CF card activity light. It's an orange one. It's right here, and it's going to flash briefly when I run that. And so that command's it takes less than a second to dump all the memory to the CF card, which is you know, pretty cool. That's going to facilitate, I think, later on in this project, some nifty things like suspend resume functionality like you have on your laptop. You know, it's pretty quick and easy to dump, you know, everything in memory to the CF card, and, you know, back up your CPU registers. You know, kill the power. Leave it off as long as you like. The CF card is non-volatile. Power it back up, you know, reload memory and set your registers and jump to the appropriate address, and you can just resume from where you were, which is really cool. You know, you absolutely couldn't do that on any, you know, any of the original Z80 home computers, you know, in the 70s and 80s, because you just did not have 64 kilobytes of, you know, very fast, very accurate, you know, non-volatile memory lying around. It just wasn't practical. But, you know, today it's super easy. And so to prove that worked, we can use CF load and read everything that we just did back to memory. I'll dump it at 4000, which is somewhere in RAM. It's deep enough into the address space that it's not going to clobber any of the RAM that the monitor program uses for, you know, reading in these commands, that kind of thing. Put in my start sector, and I'll just read the first. Oops, I can't read the first 10 sectors. Orange light blinks again, not that you guys can see it, and then I'll dump from 4000, and so you can see it starts 310080. This is the same, you know, memory that we saw earlier, dumping from 000. So it looks exactly the same. I basically just duplicated, you know, the first 10 sectors of memory, you know, a little bit further down. which is kind of cool. So you know, the CF stuff works very well. Oops, there's a CF boot command, which I'm not going to show you. What this does is reads the first sector of the disk into memory, into RAM, at the lowest possible RAM address, and then jumps to it, executes it. So this is how the you know, the first sector of disk is the master boot record, or the MBR. So this is where on your PC, you know, your bootloaders like Grub or Lilo, that kind of stuff, live, and the PC architecture machines just read that first sector and boot it, unless you've got a bootable, removable, media stuck in somewhere. That's how the computers bootstrap themselves, and this just has that same functionality. I won't do it now because, well, in theory I could, because I've just copied, I've just copied the monitor program from ROM to, no, that won't work because it won't do the first sector. Yeah, I'm not going to run that now, but it's there. That's something I'll probably use in future. And I guess the only thing now that I have not really showed you is this last command at the help listing, which is CLOad or SIRLOAD, which is a serial loading command. So I mentioned at the start of this video that I have two serial lines connecting the LM-512 to the PC at the moment. So on the second one, on the PC side, I have a small little Python script acting as a server, a file server, I guess. And when I type the SIRLOAD command, I can load out somewhere like 4000 again, say, and hit that, and you can see it's transferring bytes in blocks of 256 bytes from my PC over serial into the RAM. I can dump that, but actually it's going to look just like the last one because the PC is currently serving up this monitor program because I've been using it to sort of debug this stuff. I mean, this serial loading is actually a massive productivity boost because previously when I wanted to make a change to the firmware, I had to actually physically pry out the ROM chip, stick it in my little homemade Arduino based EEPROM programmer, program it, pry it out, stick it in, find a bug, repeat, spend the whole night kind of popping in and out. I've already actually broken one of the pins on that ROM chip and had to solder in a little bodgy replacement. It's not great, it's slow, and it's fiddly. The serial boot thing, I mean, it's great. The little Python file server, just runs continuously, and it always serves up the freshest version of the file. You don't have to restart it, so you can just, be developing, this monitor program, say, and each time you assemble it, you can just do the serial load command, and then jump to, so I can do jump 4000. This might break. No, it's worked. So it's a jump 4000, and this is now executing that second copy of the monitor, leaving elsewhere in the address space. And so it's extremely quick and easy to kind of do rapid development cycles, get rid of the bugs, and you only have to actually burn to the ROM chip every couple of days when you've made a good chunk of progress. It's super cool. Made things go a lot faster. So yeah, I guess that's probably oops, what is that command? Helpers. That's pretty much everything. I haven't shown you the bank command. That just controls the bank switching of memory, the higher 32K. That doesn't work, but I think that's a hardware thing. I think I need to get a new chip for those flip-flops for the higher address pins. But yeah, I think that's showing everything else. So that's it. I mean, it's this little monitor shows that everything is working as it should. All the basic hardware is there. The real-time clock's working. The CF card's working. The serial chip's working. Everything is happy, and you can control it all from a nice little command line interface now. The code is pretty rough and ready, so I'm going to spend some time now tidying that up and actually rewriting this so that this functionality can be accessed using BIOS interrupt calls. So you can actually generate an interrupt. Well, actually, it's not an interrupt on the Z80. It's just these reset commands, which are just kind of a very fast version of the call command, so that you execute code at a fixed address somewhere around in the address space. And this is how this is how most computers are architected. So IBM PC, for example, the BIOS the BIOS ROM code has functionality in there for accessing the keyboard, the screen, the disk, the basic stuff. and programs can use that by doing a BIOS interrupt call, kind of like system calls in an operating system, to access that behavior, and then you have something like MS-DOS is built on top of that, and it provides MS-DOS API calls using a different interrupt vector, and they kind of get this tower of abstraction layers. And so I've got to kind of formalize this functionality so there's a nice bottom abstraction layer that I can easily access from any kind of program. So that'll be kind of the next step in this project, and then I think after that, now that I can load code in using the serial line, it'll be easy to develop some file system code. So I'd like to be able to actually read like a FAT16 file system off the CF card, so I can load and save files by file name. That's going to be a maybe kind of tricky bit of coding. That's going to need some debugging, and previously when I was just loading my code off the CF card, I couldn't really do that, because you couldn't have your code just stuffed at the first sector and have a file system on there at the same time. But now I can kind of just load my code off the serial line and read the disk and write to the disk willy-nilly, and so I can kind of hopefully get a nice file system implementation written up in not too much trouble, and then I can really start doing some really cool things with this. But yeah, so it's steadily progressing. Hopefully getting towards something really cool. This is starting to feel more and more like a real computer. I'm pretty happy with how it's coming along. Okay, so thank you for watching, and see you next time.